So let's take a look at the second problem from the practice exam, which is 4.27. We have a pipe. It's acted upon by two forces, F1 and F2, along with a couple loading. These forces will tend to translate it down and to the right. This couple loading will tend to rotate it in the counterclockwise direction. And we're asked to replace this load, which consists of the two forces in the couple, by a single equivalent force couple system acting at point A. And if you recall, we said in the course earlier that this is a valuable analysis technique in terms of designing the requisite support structures at point A, because if we know that this entire loading system is equivalent to an effective force couple system at point A, we know right away what kind of support we need to put there, because it just needs to be able to overcome the translational effect of the resultant force and overcome the rotational effect of the resulting couple at that point. So we're given the magnitudes and we're given enough information to decompose these. So for these types of problems, the first thing that you want to do is just find the resultant force element of the resultant force couple system. And the reason you want to do that is the resultant force element is very simple. It's always just the vector sum of all of the forces that are acting on the body. And what that says is that from a translational point of view, it doesn't matter whether these forces are applied at any particular point. Their translational effect is the same. So we just add them kind of from a translational point of view, ignoring their point of application. So we can decompose F1, just kind of draw the force triangle directly on it. We notice it has a negative y component and a positive x component. The x component is opposite the 30-degree side length. So this is going to be F1 sine 30 minus F1 cos 30. That is F1 decomposed, positive x, negative y. And F2 has no x component and only a y component. So when I add those together, I would have F1 sine 30 for my x component, and for my y component, minus F1 cos 30, and this should be a minus, sorry. Notice that's going in the negative direction, minus F2. So plug in your particular values here. This, I got my usual, where I get the recording, something interrupts me and I have to stop the video, so you can see I had these answers in here beforehand. But what I want to do is just create a new vector where the x component is going to be magnitude F1, which was 800, times sine d of 30. And I should really, let me actually just take these separate, because we're going to need them later on in the problem, as you'll see. So F1, if you recall, has an x component of its magnitude, which was 800, times sine d of 30, and d, again, because I don't set my MATLAB, you don't set the mode in degrees like you do a calculator. You tell it that it's you're inputting a angle in degree by using that modified function. So remember, we had F1 times the sine for the x component minus F1 times the cosine for the y component. And that will give us, and I'll just write this on our .cam just in case we need it later, 400 minus 692.8 newtons. And then F2 had no x component, and its y component was purely negative, and the magnitude was 400. And we want the vector sum of those two. So we can find MATLAB, when it writes 1E03, that just means 3 orders of magnitude. So the x component is really 400 in this case, and the y component is really minus 1093. I mean, technically, let me just keep it all for now, just in case we need it. So I'll go back to the .cam and show you how I translated those. So if you use your calculator, hopefully those are the results you get. So if you notice what the magnitude of this resultant force in the angle it makes with the horizontal axis. So in order to get its magnitude, just take the square root of the sum of the squares. When you square a negative, you get a positive, but I'll show it that way anyways, that way you don't forget. And remember, in the last example problem, I told you could do that operation in MATLAB by just the norm operation. So this is going to be the three significant figures, 1,100, and let me actually just write, whenever it's in MATLAB, I tend to always, when it has that scientific notation in there, make a mistake when I try to round right away. There's a way, you might imagine, in a computer program that you can have it round to a particular precision. But for now, I will just write it out, and I will say 2 3 sig figs. That is about 1,160 newtons. So just showing you on the .cam how that looks. And then for the angle that this makes with the positive x-axis, you notice that this vector has an x component of positive 400 and a y component, which is almost like 3 times as big negative. So it's like sitting down here. This is what it looks like. So that's the angle that they want to report. And remember, you know this side length, it's just 1092.8 long. You know this side length, it's 400 long, so you can take an inverse tangent of opposite divided by adjacent, or you can let the calculator do the work for you, and since it's in the fourth quadrant, actually pass in the negative value for the y component. Whatever way you want to do it is fine. Just so you get my point, what I'm trying to say here is if you take and don't pass in a negative for your y component, you'll have to manually add that negative. But if you pass it in as negative, the calculator will recognize that that angle is in the fourth quadrant, and 3 significant figures, that is minus 69.9 degrees. And we like that the result is minus. However, we got there because we know by sketching that this is in the fourth quadrant. So that is for mag R, and this is for its angle. Okay, so we're getting close. So now the question is, what is the effective couple at point A? Well, to get the effective couple at point A, I need to add the loaded couple that's actually on here. So just naturally, there's 300 Newton meters of rotation in the counterclockwise direction. In addition, both of these forces, at least a component of this force, along with this force, will tend to induce a rotation about point A. So if you remember, when you translate these forces to another point like point A, what's really going on here? Well, let me actually just show you 2 things here first. Hopefully everyone gets, one, that F1x doesn't contribute to rotation about A. And the reason being, if you decompose this at the point of application into an x and a y component, note that the line of action of the x component goes directly through A. And I'm writing this down just because I'm going to scan these as well. Not like this will be particularly meaningful if you didn't watch the video. But that horizontal component has a line of action that goes directly through A, so it won't actually induce any rotation about point A. However, the y component will. So let's look at how to find the equivalent moment of F1y. And it's the same idea for F2. I'm just showing you why this works the way it does. You actually don't have to worry about this. When you're actually doing the calculations, you just compute the moment of any relevant force about A, and you assume that that's a couple that you can add to the couple that's already loading this pipe. But here's why that works that way. If this is point A, and this is like my perpendicular distance of 0.75 meters, and this is the y component of F1y, of F1, I can always add equal and opposite forces here at point A without changing the underlying mechanics of this body. So these are equal and opposite. I didn't really change anything, but notice what the upward force that I added and the original downward force here do. These form a couple. And that's why when you translate for example, the y component of F1 to point A, it is equivalent to just moving the force directly down and adding on a couple, which is equivalent to the magnitude of the force times this perpendicular distance. So that's what's going on under the hood. But technically, what you're doing here is you're computing the moment of the forces, so summing the moment of the forces about point A. And that is the reason that works the way it does. So if you think about it here, you're going to have the y component of F1. So let's counterclockwise positive traditionally. It's going to be the y component of F1. And then what is going to be the perpendicular distance in this case? That line of action has a perpendicular distance of 0.75 meters. Pin at point A, translate downward like the y component, and notice that rotation is in the clockwise direction. So that will actually be assigned a negative sign. And you can do the vector approach in order to show that is minus k hat when you have I hat cross minus j hat. Remember our 3 unit vector circles. You can go back and show that. But by the same logic here, F2 is going to induce clockwise rotation, so it will be negative. but it's going to have a perpendicular distance of 2.25. In addition, don't forget that this had a couple. That's so. Remember when they just draw like kind of this circular arrow here, what they're saying is that that's a couple. So it's a free vector. It can be moved anywhere or added anywhere. And since it's in the counterclockwise direction, it's positive by our sign convention. What it's doing is counterbalancing the rotation of these two forces in the clockwise direction. So I should say, sorry. That's very, very be careful. Do as I show, not as I say there. So these, I think I said it right. Actually, I kind of freaked out. But anyways, these two applied forces are going to tend to rotate in the clockwise direction, right? And if you notice, this is tending to rotate in the counterclockwise direction by the way the arrow is shown, counterclockwise direction. So everything is right on here. So we're just summing all those up. So what would that be? Well, the y component of F1, we had it up here already, is going to be that minus 692.8. Remember, we've hit this a couple times, but don't double minus yourself. If you kind of determine what these signs should be based upon the rotational based analysis that we just did, don't go ahead and plug in a negative for there again and make it positive. The key point being, you just want the magnitude of this since you assign the clockwise rotation by manual inspection. In the same fashion, F2, I wouldn't use the value of minus 400. I'll just use 400 here because I've manually made sure that that result rotates in the clockwise direction. So I'm kind of throwing my units away. It's important sometimes when you do these problems where you have an applied couple to make sure that the quantities that you're multiplying together give you the same units as the applied couple, Newton meters, and they all do. So we're good here. So let's just actually compute what that is. So let me just make sure I have that F1x, that way I don't have to round. Sorry, I should say F1 of 1. Good. So that is the sorry. It's the second component of F1, the y component, which is at minus 692.8. So that is good. So I want to multiply, and you can round it. That's okay. Just don't want any of your rounding errors to kind of carry on and result in a final rounding error. So it's remember that that has a negative sign in there. Actually, let me just, sorry, it's late. Type what I have on the paper written directly, and then I'll show you how to make this calculation symbolically if you're interested. So minus 400 times 2.25 plus 300, and that will come out to be minus 1,196, 1,100 and, sorry, minus 1,119.6, I should say, Newton meters, and we'll do the rounding in a minute. But what I was saying there, if you do this symbolically in MATLAB, if any of you are, remember that when you define your vector F1, it has that negative component in there. So when you write the multiplication using that, don't put another negative in, or you will undo basically what trying to do. You notice you get the same result if you leave those negatives out. That's what I was trying to say by that. Oh, good. Okay. So anyways, if you wanted to round this to 3 significant figures, so if you see how I got that number that I wrote, just shift this decimal by 3 places, 1, 2, 3, and it will be 1,119.6, which is what we have written on the document. And it is negative, indicating that it's a clockwise rotation, not particularly surprising, given that we had such strong counterclockwise rotation induced by the two applied forces. So if you wanted to round that to 3 sig figs, it would just be minus 1,120 Newton meters. And that is the effective couple of the force couple system about point A. So hopefully that made sense to everyone. Hopefully it was helpful. Sorry for the little bit of stumbling on the calculation there. Sometimes when you're trying to record these in real time and look across a bunch of different screens and write down, it gets a little bit confusing. But that shouldn't be too hard of a problem. I'll give you one like that, but it won't be that one exactly likely. It'll be the same underlying principles, though. The one thing I did want to mention is if you're asked, sometimes these problems in the book basically ask you where you could apply this resultant force to reduce the force couple system to just a force. So if this system were to be translated to a single force couple acted at A, this would be the resultant force, and this would be the couple. What you would find is, since this resultant force system is going to tend to induce clockwise rotation, you could basically take this resultant force vector, find its y component, and you could find the distance that you need to move it from A in order to induce this rotation. So what you would say is that this d is basically going to be equal to the rotation that you need to induce, which is 1120, divided by whatever the y component of that resultant force is. So it would be 1120 divided by 109.2.8. And that would be, let's just compute it real quick. 1120 divided by 192.8, 1.02 meters about. So what that is saying is basically, if you replace the two forces and a couple by an equivalent force couple system acting at A, you need this resultant force in this couple. However, if you just applied this resultant force 1.02 meters away from point A, that would have the same effect as the original two forces and couple. So all three of those, either the original thing, this at A, or a single resultant force applied at D, would induce the same translation and rotation of that pipe. So if you do happen to get one of those questions on the test, just know how to compute that distance. And I don't think it's too big of a surprise, because we did talk about a problem like that I recorded a video, so I think it must have been one of the examples that we did in a learning module in chapter 4.